Download this code from codegive.com, link in the description below. Certainly. Kernel density estimation, KDE, is a non-parametric way to estimate the probability density function of a random variable. It is particularly useful for visualizing the distribution of data points in a continuous space. What is kernel density estimation? KDE works by placing a kernel, a smooth, continuous function, on each data point and then averaging these kernels to produce a smooth estimate of the density function. The choice of kernel and the bandwidth, which controls the width of the kernel, are crucial as they can significantly affect the resulting density estimate. Key concepts: 1. Kernel, a function that defines the shape of the distribution to be placed at each data point. Common kernels include Gaussian, normal, epanechnikov, uniform, triangular. 2. Bandwidth, h, a smoothing parameter that determines how wide the kernel is. A small bandwidth can lead to overfitting, too much detail, while a large bandwidth can lead to underfitting, loss of detail. 3. Non-parametric, unlike parametric methods, KDE does not assume any specific functional form for the distribution. Steps in KDE: 1. Choose a kernel function. 2. Choose a bandwidth. 3. For each data point, place the kernel centered at that point. 4. Average the contributions from all kernels to get the estimated density. Example: kernel density estimation with Python. We'll use the Python libraries NumPy, Matplotlib, and Seaborn to demonstrate KDE. Step 1. Install required libraries. If you haven't already installed these libraries, you can do so using pip bash pip install NumPy Matplotlib Seaborn. Step 2. Generate sample data. Let's create a sample dataset using NumPy. Python. Import NumPy as np. Import matplotlib.pyplot as plt. Import Seaborn as sns. Set a random seed for reproducibility. np.random.seed, 42. Generate sample data, 1000 points from a mixture of two normals. Data 1 equals np.random.normal, loc equals -2, scale equals 1, size equals 500. Data 2 equals np.random.normal, loc equals 3, scale equals 0.5, size equals 500. Data equals np.concatenate, data 1, data 2. Step 3, visualize the data. Before applying KDE, it's good to visualize the raw data. Python. plt.figure, fig size equals 10, 6. plt.hist, data, bens equals 30, density equals true, alpha equals 0.5, color equals gray, edge color equals black. plt.title, histogram of data. plt.slabel, value. plt.elabel, density. plt.show. Step 4, apply kernel density estimation. Now, we can use Seaborn to apply KDE and visualize the estimated density. Python. Create a kernel density estimate plot. plt.figure, fig size equals 10, 6. sns.kdplot, data, bw_adjust equals 0.5, fill equals true, color equals blue, alpha equals 0.5. plt.title, kernel density estimation. plt.slabel, value. plt.elabel, density. plt.show. Step 5, adjusting bandwidth. You can adjust the bw_adjust parameter to see how it affects the KDE plot. Python. Different bandwidth adjustments. plt.figure, fig size equals 12/8. Original bandwidth. plt.subplot, 1, 2, 1. sns.kdplot, data, bw_adjust equals 0.5, fill equals true, color equals blue, alpha equals 0.5. plt.title, bandwidth equals 0.5. plt.slabel, value. plt.elabel, density. Larger bandwidth. plt.subplot, 1, 2, 2. sns.kdplot, data, bw_adjust equals 2, fill equals true, color equals orange, alpha equals 0.5. plt.title, bandwidth equals 2. plt.slabel, value. plt.elabel, density. plt.tight_layout. plt.show. Conclusion. Kernel density estimation is a powerful technique for estimating the probability density function of a dataset. It is especially useful for visualizing the distribution of data and can help identify underlying patterns. By carefully choosing the kernel and bandwidth, you can create a smooth representation of your data's distribution. Further reading. Books. The Elements of Statistical Learning provides a deeper theoretical understanding of KDE. Research papers. Look for papers on non-parametric statistics for advanced topics. Feel free to explore different datasets and kernels to see how they impact the KDE results.